11.3, one-sided limits and continuous functions. So if you've watched some of the extra videos, you've probably already started thinking about one-sided limits, and continuous is a word that we worked with a lot in Chapter 1, and I've been using it the last couple days. We've been kind of talking about it all year. So we're just putting a lot of pieces of things together today. So in our example function here, for example 1, we've got a piecewise function, and that's because we have an equation when x is less than 1, we have an equation for x greater than or equal to 1. And we're going to look at this function, and we're going to find the limit going to 1 from the left. That's what that minus sign means. It means from the left. So the limit as x goes to 1 from the left. And then there's this one with the plus sign, which means from the right. So we're going to find the limit as x goes to 1 from the left and from the right. And then we're going to look at just the limit of f of x as x goes to 1. So let's go ahead and look at from the left. So left would mean literally that way. So that means I go to the very far left-hand part of the graph and I trace the function. As I get closer and closer to 1, it looks like my y is approaching 2. So this is going to equal 2. When I am looking at as x goes to 1 from the right, that means literally this way from the right. And so I would trace this far right-hand side of the function down until my graph is about equal to 1, and it looks like the y is 4. So this one's going to have a limit of 4. So on a graph like this, I mean, we're tracing on both sides. We're kind of expecting them to meet up in the middle. Like the limit is only one number. It can't be 2 and 4 at the same time. So because the left does not equal the right, the limit here does not exist. So that means does not exist. And we want to add a little bit of extra stuff in here. We want to add that for this limit, if the left equals the right, then it's the same. But we don't have that here, and so the limit does not exist. So because one of those limits coming from the left, it was 2, from the right, it was 4, we can't get that to agree, and so we don't have a limit in that case. It does not exist. So this brings us to an idea, kind of a throwback here, thinking about continuous functions. So the real issue was that function was not continuous, right? That was part of the problem. And we looked at a lot of different looking continuous functions earlier this year. The first 2 we definitely had names for. The third one is kind of a weird combination thing that's going on. But this first one, I have a hole at A. And then I think, first of all, we probably need to take a step back and think about what is continuous. Continuous means we can trace with a pencil without lifting up. So the problem with this first one is I can trace to the left up to A, but then it can't actually equal A, so I have to lift up my pencil, and then I have to do this part. So there's the hole at A. So that's removable discontinuity. So it's definitely not continuous. These are all some kind of not continuous function. And the interesting part here is that the limit actually does exist, though, because as I approach A from both the left and the right, they're going to settle in on that same y value. So the limit of f of x exists. But our f of a is undefined. So again, we're just kind of looking for clues about how to actually define a continuous function. How can we tell if something's continuous? Well, this one's definitely not. We have a limit, right? So having a limit alone is not proof that something's continuous. In this case, we have a limit, but there's a hole there, so f of a is actually undefined. So the second one, my function is defined all the way through, right? I don't have any issues. I can find f of a. F of a exists, but in this case, my limit doesn't exist, does it? Because when I'm going to the left, it's going to be this number. When I'm going from the right, it's going to be that number. So in this case, oh, and I'm supposed to be using f of a, right? Because we're pretending we're plugging in an a. So in this case, my f of a is part of the domain, f of a exists, but the limit of f of x does not exist. So still not continuous. This is actually jump discontinuity. So we have removable, we have jump, and then this is kind of a weird thing. It's like a removable discontinuity with the hole over there removed. So this one's still not continuous, because when I trace, I have to go here and then jump up to the point and then go back to the function. So still not continuous, but let's think about what's going on here. So this time we do have a limit. We have a limit as x goes to a of f of x. So the last one we didn't have a limit. The first one we did have a limit. So we kind of swapped some pieces from either one of those. So this time our limit exists. F of a exists. But our issue is that they're not the same. So the limit as x goes to a of f of x and f of a are just not even equal. So all of this is to give us an idea about how to decide whether or not a function is continuous, because we really care about stuff like that. Just like we care whether or not something's actually a function, we also care whether or not it's a continuous function. So continuous functions are just something that's going to make math work better if I don't have to worry about all this weird stuff going on. So this brings us to our definition of a function that is continuous at a number. And so this is a pretty long definition. We're going to put it in our own words. So a function is continuous at a if the first one speaks about a being in the domain. So when we think back at the examples we looked at, the first one had a hole there. A wasn't even in the domain. So a does need to be in the domain. The limit has to exist. So our second example, we didn't even have a limit. So the limit does have to exist. And then the third issue is that value of f of a has to actually equal the limit, right? And that was our issue on the third one. So the third one, we had a limit. We had a as part of the domain, but they weren't actually equal. So our limit has to equal that actual value when we plug it in. So those are the things that we have to be continuous. So there's going to be a lot of functions that we look at in the homework where you're just going to know they're continuous. When we have the equation of a line, you're going to just be able to say continuous right away. You don't really have to show any work. You can just write it's a line, or you could write it's a parabola, continuous. But there are going to be some kind of weird functions where maybe we have to think about it. But our writing and the way we're going to prove some of these things are not going to be as lengthy maybe as what the book does. So I want to make sure we go through it. So whenever we're looking at a function here, we're going to decide two things. We're going to decide if it's continuous at 2 and at 1. So we're going to do two parts. And whenever I see a rational function, I always factor. So we want to make sure to do that. And lo and behold, there's a 2x plus 1 there. You're probably used to no coincidences on factoring like that. So our f of x is equal to 1 over x minus 1. Okay, so I need to first decide if it is continuous at 2. So when x equals 2 is what we're checking for. So it looks like in my original function, 2 is in the domain, right? My domain would be numbers except 1 and negative 1/2. So those would be those bad numbers. So it is in the domain. 2 is in domain. Check. And I can plug 2 in. So I know that I could find f of 2, and I know it's going to be the same thing as the limit. So my limit as x goes to 2, and I could choose to do the first equation. I could choose to do the second one, the simplified one. Is going to be 1 over 1. It's going to equal 1. So I do have a value, and it would be the same thing as actually taking the limit. So I'm just going to write, what am I going to write? Limit equals value, I guess. And check. So we're good to go. So how about for B? So you can see we're really not showing nearly as much work as it sounds like it could be. So how about at x equals 1, or when x equals 1? So what I noticed right away is 1 minus 1 would be bad in the denominator. So 1 is not in the domain. So we don't have to check any farther. I don't care about the limit. I don't care about you figuring out what f of 1 is. Well, we can't even find f of 1, can we, if it's not in the domain? We just know it's not continuous. Not continuous. So just to keep up with our graphing skills, I do want to take you through the graph of this really fast. So if I'm graphing 1 over x minus 1, it's like the graph of 1 over x, but I've moved it. So I have, let's see, I guess we could go through our x-intercept, y-intercept, we could do it that way. So x-intercepts come from the numerator, there's none. My x-asymptote, we're gonna just stop the word right there, comes from my denominator, so that would be x equals 1. So I'm gonna go over to 1 and make a dashed line. My y-intercept comes from letting my x equal 0. So 1 over 0 minus 1, 1 over negative 1. So negative 1 is my y-intercept. Okay, and then my y-asymptote, it is bigger on the bottom. So y equals 0. And by bigger on the bottom, we mean x is to the first power in the denominator, and there's no x's at all. So there's a bigger degree in the bottom. So let's make a dashed line at 0. And this is not really necessary, but I just think that this is a different kind of function we haven't graphed lately. I know that these kind of functions are pretty symmetrical. I have a point here, so I'm going to go ahead and connect. And then what I have to remember, though, because I crossed out the two x plus 1s, is that I have a hole at x equals negative 1/2. So I need to remember about that. So I'm going to go over here to about negative 1/2 and make a hole. And then here's this part of my function. The other part is symmetrical. And so I can see there's a reason that 1 is not in the domain. At x equals 1, I actually have infinite discontinuity. And so I've got one part of my graph going up to positive infinity, the other part of my graph going down to negative infinity when x equals 1. So no wonder 1 was not in the domain. So we always want to kind of have a picture in the back of our heads when we're looking at these problems. That's the real key today. So for example 3, we want to determine whether or where, a piecewise function is discontinuous. So we're always worried about those points like 0 or 1, where the function changes. Instead of using this one, now you're using this one. So we're going to check x equals 0 and x equals 1. Those are going to be the interesting points where all the weird stuff happens. So at x equals 0, this first function is x plus 2. So that would be 0 plus 2 or 2. The second function is just the number 2. And those are both the ones that share the 0, right? These two share the 0. So the second one is just 2. And since 2 equals 2, they match. We would say it's continuous. And we're basically doing this like we did before. Just bigger vocabulary, right? And maybe a better understanding of what's going on. So we would say continuous. We also want to look at x equals 1. So let's check that out. And then this time, maybe I should use a different color. I definitely want to erase this and get it out of the way. So when I'm looking at x equals 1, now I don't have to worry about that first part of my function, x plus 2. That was only when x was less than or equal to 0. So the two that share the 1 are the middle one and the last one. I guess I didn't switch color after all. So this middle one at x equals 1 is just 2. And then if x is greater than 1, I would do 2 squared plus 2. Or sorry, I'm using 1, aren't I? I wrote down a 2, and then I just wrote down a 2 again. So we would have 1 squared plus 2, which is 1 plus 2, which is 3. So my function jumps between those. So I actually have jump discontinuity at x equals 1. So it is discontinuous. I'm going to put jump in parentheses at x equals 1. So you can see the kinds of functions we have to worry about are piecewise. We definitely have to worry about those. We have to worry about anything that's a fraction because we could have infinite discontinuity. And we have to worry about when we cancel out a common factor because those are going to give us wholes. So those are really the 3 things that we do need to worry about with discontinuity. And then let's just go ahead and graph this one too, just because it's kind of a weird function. I think I can get a graph picture on here. graph. Let's go ahead and pull up a graph. Sorry, this is so slow. This is not really a critical part of our notes, but I think it's just always good, like I said, to have a picture of what's going on. And I just put the picture on the wrong page. Let's try it one more time. All right, so let's go ahead and try graphing that. So we had x plus 2 if x is less than or equal to 0. So here's the 0. X plus 2 means I'd start at 2. I go back the other way, and it would be a solid filled-in circle. I had y is 2, or f of x is 2, between 0 and 1, and it's or equal to 1. So this is 2, so I'd have an open circle here, and then it would go to 1. Okay, and then the third part of my function is x squared plus 2 if x greater than 1. So here's 1, x squared plus 2 means I would start my parabola here, and then I would go up 1 over 1, so this would be that first point, and then up 3 over 1, and then up 5 over 1. So here's my parabola part right there. So it's just, I think it's good to see that picture where it's definitely jump because I can trace this part and I trade from one function to the next, but I don't have to pick up my pencil. I go right to the other. But then here I actually have to jump and I have to do this part of my graph. So like I said, I think it's just good to kind of have a picture of what's going on in our heads. And I do think this year that we've just not had the time to maybe practice some of these skills as much. So it's good to see that. It's good to see someone just work it through again and get a reminder. So for much of your homework, you're going to be looking at whether or not something's continuous or what's going on. If it's something easy like a line, you know right away. You really have to worry about factors that are canceled out. Those make wholes. We have to worry about piecewise functions because we could have jump, and we have to worry about rational functions where we have infinite discontinuity. So that's really what we have to worry about.